All right. Last time we were talking about Riemann integrals over rectangular regions and iterated integrals, and there was a question towards the end about what happens if the domain is not, in fact, rectangular. So we're going to talk about that for a bit. So let's go back to Calculus 1 for a second. Suppose that we were given a drawing of a region between two curves. The lower function given by y equals g of x, and the upper function given by y equals f of x. And we were asked, how do I compute the area between these curves? The way we would do this is by breaking up the region into very thin slices. Each of these slices would have a given area, and we would add up the area of each of those slices. So this slice in particular, let's analyze it. It is at some point x on the number line. The height of the rectangle is f of x minus g of x. Its width is given by some delta x, depending on how thinly we cut the slices. And so the area of the rectangle is fx minus gx delta x. And then we sum over all the various different slices, which, as delta x gets smaller and smaller, approaches the integral of f of x minus gx dx. As for the bounds of integration, those are given by the points of intersection between the two functions here at some points a and b. And so we go from x equals a up to x equals b. And this allows us to compute the area of such a region. The question is, how do we turn this into integrating more generally a density over a region, and therefore, instead of an area of the region, the mass of that region? We can think of area as the integral of a density of 1. And our mass as an integral of some changing density function. And so if we wanted to compute the mass of this same exact image instead of the area of the image, we're going to do the same exact analysis going slice by slice. So that same slice rather than computing the area of that slice, we're going to compute the mass of this slice. We can think of this as a particularly thick line. If you were to go along a single line, you can compute the mass of that line, and that would be given by an integral. It is a one-dimensional thing, so it's going to be a one-dimensional integral going from the bottom to the top. Down here, we have e of x. Up here, we have f of x. And so we're integrating from the y value of g of x up to the y value of f of x of the density function. Here, x is a fixed value, and we're integrating over y. And so this is the mass of the line. If that's the mass of our line, then the entire slice is just the mass of that line multiplied by the width of that slice. And so the mass of the slice is going to be given by the integral from y equals g of x up to y equals f of x of delta x y dy times the thickness of the slice, delta x. In the same exact way that we extrapolate from the sum of fx minus gx times delta x to the integral of fx minus gx dx, we sum up these slices. So we take the sum of these slices, giving us total mass should be approximately the sum of these integrals. Delta x, which then in the limit is going to become the integral, again, from a to b. This time, again, specifying x equals a to x equals b of the integral from y equals g of x to y equals f of x of delta xy dy, and the delta x turns into a dx. Thus giving us an iterated integral, but rather than having constant bounds, which would give us our rectangles, we have this functional bound for the internal integral. Questions? Let's go through an example. So suppose we were asked okay, suppose we were asked to find the mass of the region bounded by the functions y equals square root of x, y equals x squared, with density given by delta of xy equals x squared y. First thing we're going to want to do to help us along is draw our graphs here. So we've got y equals square root of x. It looks something like this. Sorry, y equals x squared, looks something like this. And y equals square root of x, looking something like this. Each of our slices are going from base y equals x squared up to y equals square root of x. So the internal integral is going to go from y equals x squared up to y equals square root of x of our density, x squared y dy. That's our internal integral. And then the external integral, we need the bounds of x ranging from here at 0 up to here where they intersect, which we have to solve for, meaning we need when y equals square root of x and y equals x squared simultaneously. That is, square root of x must equal x squared, and so x to the fourth equals x, or x cubed equals 1. And so x equals 1. And so that point means this point over here is at x equals 1. With that in mind, we get our bounds for x from x equals 0 up to x equals 1 dx. We now have everything set up. We should be able to do this using regular integration techniques. So we integrate from 0 to 1. I'm going to pull out the x squared because x squared is a constant in terms of y. And so we get the integral from y equals x squared to square root of x of y dy dx. Jumping ahead a little bit, we get the integral from x equals 0 x squared. After evaluating this integral, what we're going to get is x over 2 minus x to the 4 over 2, which would give us the integral from 0 to 1 of x cubed over 2 minus x to the 6th over 2 dx, which, evaluating, is going to give us 12. And so we take the equations that were given, we draw the graph, identify the bounds for our integral, evaluate the internal integral first, which allows us to integrate the external integral. Questions? All right. Let's try another one, which has a little bit of a twist to it. So suppose we were given the following. Find mass. Actually, let's do it another way. Suppose we're given the following. Integrate from 0 up to 8 from cube root of y up to 2, the square root of x to the 4th plus 1 dx dy. As it's currently set up, we have x as the internal integral, which means our bounds are from y equals 0 up to y equals 8, and x equals the cube root of y up to x equals 2. The problem with this current setup is our internal integral here requires us evaluating the integral of the square root of x to the 4th plus 1. And there is no good way to evaluate such a function using elementary functions. There does not exist an antiderivative for the function square root of x to the 4th plus 1. It just doesn't exist. So what we have to do is switch the bounds of integration, which was nice and easy when we were dealing with rectangular regions, but it's much more complicated when we don't. And so what we're going to have to do is first draw out the region that this depicts. So we have y going from 0 to 8. That's nice and easy, going from 0 up to 8. X is going from the cube root of y. In other words, y equals x cubed. And so that's going to look something like this. And stopping at x equals 2. going from this function up to this function. This time using horizontal wedges rather than vertical wedges. Since integrating in this fashion doesn't work, we transport it into the region, stop using horizontal wedges, start using vertical wedges instead, and reform the integral using this perspective. And from this perspective, we're no longer going from x equals the cube root of y up until x equals 2. That would be the horizontal slices. Now, instead, we're going from down here at y equals 0 up to here at y equals x cubed. And so our internal integral is therefore the integral from y equals 0 up to y equals x cubed of the same internal function, square root of x to the fourth plus 1, dy. As for the external integral, our bounds are the bounds on x, and x can range from all the way over here at 0 up to all the way over here at 2. And so we get x equals 0 up to x equals 2. And that would be dx. What you should note about the function here is that there are no y's in this function. And so we can pull that completely out of the internal integral, leaving us with the integral from x equals 0 up to x equals 2 of the square root of x to the fourth plus 1, the integral from y equals 0 to y equals x cubed of absolutely nothing, just dy dx. And so this integral, we're integrating 1, is just going to give us the length of the interval, leaving us with the integral of x equals 0 to x equals 2, square root of x to the fourth plus 1. The length of the integral is x cubed dx. And now, instead of having to integrate x to the fourth plus 1, we have to integrate the square root of x to the fourth plus 1 times x cubed, which gives us precisely the factor we would need to do a u substitution. And so we'd be able to convert using u equals x to the fourth plus 1 into getting the integral from 1 to 17 of the square root of u du over 4. Computing this, we would then get 1/6, 17 to the 3/2 minus 1. And so the technique is you start out with an integral, you don't know how to do it, convert it into a picture, switch the perspective from dx dy to dy dx, turn that into an integral. This you can now compute. It doesn't always work, mind you, but it is a good technique. Questions? All right. Now, with that, we move on to our last example, which has a different problem. Suppose that we wanted to compute the region bounded by y equals 1/2 x, y equals 2x, and y equals 3 minus x. After a quick sketch, we end up with a region looking something like this, giving us a triangle with vertices the origin, 2, 1, and 1, 2. And then, of course, we also have to be given the density function, which doesn't really matter for the purposes of this conversation. We'll put it as xy. The problem that arises with a diagram like this is that you're not integrating from a function to a function. If I were to try to draw my vertical slices, then over here, I'm going from the function y equals 1/2 x up to y equal 2x. But the vertical slices over here are going from the function y equals 1/2 x up to the function y equals 3 minus x. And so that means there's no way to write this as the integral over one function to another function, because it changes which function you have as your top halfway through. The same exact problem occurs if you try to use horizontal slices. Because here we're going from the left at y equals 2x up to the right of y equals 1/2 x. And up here, we're going instead from y equals 2x up to y equals 3 minus x, neither of which work as one single continuous function. And so what we have to do, not continuous, smooth. And so what we have to do is we have to break up our picture into multiple pieces. Rather than integrating this as one chunk, what we're going to do is split it in two. So now rather than having one triangle, we'll have two. The triangle on the left-hand side and the triangle on the right-hand side. We'll compute the mass of each of those two triangles separately and then put them together to get the mass of the whole. In this particular case, that would mean on the left, we're going from the function y equals 1/2 x up to the function y equals 2x, with the x values ranging from 0 at the start up to here, which has an x value of 1, of the density, dx dy dx. That would give me the area of the left triangle. And then separately, I would have to integrate the other triangle, which has bounds from y equals 1/2 x up to y equals 3 minus x. And the x values ranging from x equals 1, picking up where this one left off, and going up to x equals 2, with the same internal function. And that one gives me the area of my right triangle. And then finally, after having computed both of those, we would add them together to get our total area. And so those are the basic ideas of how we tackle non-rectangular regions. Some weird things can happen to make us break it into pieces or shift our perspective, but no matter what we do, there's always some technique for changing it back into just a basic integral techniques. Do I have any questions? All right.